speech left. The next one is going to be given by Stefano Grivet, which will describe the research activities in the fields and circuit research area.
Okay. Can you switch to the slides, please? Okay. Okay, so the last slide is the perfect launch for my presentation, because Maxwell invented some equations, and our group is titled, the code name is EM Fields and Circuits, Campi and Circuiti. So, the mission first, fields and circuits, there's three basic areas. So our mission is to characterize, model, and simulate fields, circuits, and their interactions. So I will structure my presentation with these three main topics in mind. First of all, fields, what to do with fields. With the EM fields, our expertise is mostly concentrated on analytical and numerical modeling, mathematical tools for analysis and design of, in general, electromagnetic structures. At the circuit level, mostly, we have seen circuits before in other presentations. In our case, we have a specific expertise on application of nonlinear dynamics for specific structure, which I will be describing in a second, for modeling and understanding complex systems, even biologically inspired systems. And then interaction between these two objects, interaction between fields and circuits, also named EMC, electromagnetic compatibility, which was named several times before earlier today, which basically aims at characterize and model or predict the interference that fields and circuits may have at any level, and also CAD for EMC and compliance. Now, before going to the technical part, let me show the family picture. So this is the family. I included everybody, so not only staff people, but also research assistants and PhD students, all mixed up with no order. And to keep the audience alive, I know that you're kind of sleepy at this time of the day, so let me play a little game. So you have to guess who is Mr. X. Any suggestion? Who's missing? Well, Mr. X is Flavio Canavero, who is now director of the doctorate school of this university. Now, how about Mr. Y?
We need some suggestions, come on.
He's not director. Mr. Y is Professor Civalleri, who is now retired, but who is now being appointed by the emeritus professorship position, who is very prestigious. And Mr. Z, well, you guessed it, is number one. Yeah? He's director. Okay. So this is the family. We have 12 faculty members, 6 PhD students only at this time, and 7 research assistants. Now, facilities, this is not comparable at all with what we've seen in Andrea's presentation. We have some instruments to do time and frequency domain measurements, mainly targeting signal integrity and EMC applications, mainly intended for validation purposes, because our main expertise is on modeling, not measurements. So, although this is a fast-growing research facility, our core business is modeling characterization. So this is our know-how that we can provide as a service, maybe, or as a collaboration with other groups at the department level, or university level, or international level as well. Any aspect of circuit theory at the fundamental level, electromagnetics, and in general applied mathematics, because when you formulate circuit or EM problems, you need to solve equations, and these equations can be partial differential equations, or integral equations, or even with special formulation, these sort of strange equations which are functional equations in the complex field, with complex variable field, possibly multivariate. There is a great deal of theory approximation knowledge and system identification, because as we will see later, we need to build models for complex objects, and the models to be usable must be compact, and so we need to approximate somehow the behavior of real systems. Of course, we do some frequency domain and time domain measurements to validate, and in the circuit-oriented part, there's a strong background on nonlinear circuits and systems in general, and networks, I would add. with some applications in mind being mostly analog computing and image processing in real time. About tools, of course, we do have general purpose tools like MATLAB or SPICE or circuit solvers. This is legacy tools. We also have various commercial tools for numerical electromagnetics or multiphysics, mostly used for validations now, because our core business, again, is to build tools, to formulate problems, to solve problems better than the state of the art is allowing at this time. So maybe we use commercial tools to show that our formulations are better, maybe 10x or 100x faster with the same level of accuracy. I will now go through the presentation for the three main subgroups. For each of them, I'll show you the pictures. You recognize here Professor Graglia, Daniele, and Lombardi, the staff people for this subgroup, named EM Modeling and Applications, where this is where most of the expertise in both analytical and numerical techniques, finite elements, method of moments, or Vinov methods, spectral methods, for the solution of the EM field problems, with specific emphasis on high-order numerical tools, fast solvers, numerical, but all basic arguments that are needed to solve efficiently field problems. For a broad range of applications, any instance, whenever you find a problem in electromagnetics, then you need either analytical or numerical methods to solve it, and this is where the expertise is. For various applications, including EMC, propagation, scattering, and diffraction, intentional interference, may be that you can build weapons that shoot EM pulses that can destroy even objects. Security in general and science for peace, down to more standard activities like design of microwave components. Just to give you an idea, I'm just trying to oversimplify here, but just to give you an idea, if you consider this structure here, you see a number of geometric features. You see tips, you see corners, sharp corners. So it turns out that if you want to solve the EM field equation, Maxwell's equation in these structures, the solution exploits some singular behavior, may exploit some singular behavior. And since the key for any good solution is a good representation of the problem, a good choice of the unknowns, then the question is how to choose the basis functions that you use to discretize Maxwell's equations and to solve them efficiently. So there is a lot of activities going on in choosing the good basis functions that allow the least number of unknowns to solve a problem with a given accuracy. And you see here an academic 2D structure, you see here a template 3D structure, but you think of scaling up maybe to an airplane or to a ship. So you will be millions or billions of unknowns, and if you use as less unknowns as possible, then of course you're winning. So this is basically numerical aspects of activities. About analytical modeling aspects, analytical modeling is very important because the solution of even what looks like as an academic problem may give you a lot of insight in the structure of how this structure responds to EM fields, illumination, and then you can use this information to design objects with a particular performance. So in this case, you see a wedge, for instance, a wedge problem, which is a template, a geometrical template for what most man-made structures are. They are not curves, they're not smooth, but they're rectilinear with corners and edges. And it turns out that if this object is penetrable, if the field can penetrate inside, the field problem is very difficult to be solved analytically. And so significant research activities have been carried out in this field to find optimal methods, including spectral techniques and Vinov methods that allow to solve completely with no approximation. The key here is no approximation, this field problem. Another application, both analytical and numerical techniques, is to detect objects. Maybe you want to detect some buried unexploded ordnances or a bomb that is underneath soil or a complex media, and you want to do it electromagnetically without making explode, of course. So there is a number of activities, both numerical and experimental, going on to do this. I will not comment too much about partners. For all groups here, we have significant funding from both public and private institutions and a number of collaborations. These will be found in the slides that you can see published in the department website. Now let me turn to the EMC group. You see the staff people on the top, Fabio Canavero, Ivan Maio, myself, and Igor Stefano, plus PhD students and research assistants in the bottom. I would say there's three main streams that form our main activities in the MC area. The first one is on the top here, modeling of devices, interconnects, discontinuities in high-speed information communication systems. You may know that electrical interconnects like connectors, this picture, or traces that carry electrical signals are the most important factor limiting the performance of this system. It's not at the digital level, it's at the interconnect level. When you launch systems, you want to communicate between parts of the system. These parasitics of this object kill the performance, really. So you need to assess very, very well what is the effect of these parasitics on the real performance of the system. So this is one area. The second one is modeling tools and verification for DMC of specifically applied to transportation systems, railways, cars, aircrafts, etc. You see here a railway structure as an example. And the third one is statistics in general and modeling design uncertainty and EMC effects. Of course, real objects are complex and you cannot model everything deterministically. So you need to choose some variables, and these variables will always subject to some variability, and you need to assess the variability precisely. And this is what we do in this field, and I will show some applications later. I had to choose, in order to avoid the long list of applications, I had to choose a few of them, just giving highlights. Then, of course, you're free to talk to me or to other people in the group to have more details. Now, the first I'm going to talk about is about identification and reduction of interconnect models, mainly for computer-aided design. So basically, if you want to characterize what the connector does or an interconnect does to the signals, you need to solve essentially Maxwell's equations in this complex geometry. There's many ways to do it. You can do it numerically, you can discretize the PDEs, you can come up with a partial or a linear system or an equivalent circuit, which typically for real structures has millions or billions of elements, right? So when you want to simulate this object in a system level, you put it together with other objects and you need to simulate maybe with SPICE to see what the signals look like. You cannot do it. SPICE cannot do it, it's too large. So it is possible to reduce the order, to compress the size of the system, come up with a 100x or 1000x smaller circuit, which preserves the accuracy, through suitable mathematically defined projection or truncation procedures, and we develop these kind of techniques. Alternatively, you can start with measurements, talk to Andrea, get the S parameters from his measurements, and you can identify models, dynamical models, equivalent circuits, small size, compact, that you can use again for system level simulation. These activities, let me mention, that have been producing a spin-off company, which is now actually quite successful. Still in the behavioral or approximate modeling. The first slide was linear structures. Now we go to more complex systems where you have interaction of distributed nature system, EM fields, which may couple to a cable. The termination of the cables are a transmitter or receiver, may be placed on a vehicle or an aircraft. The received signal is affected by this interference. So how can we model the entire system in a compact way? So this is a typical application of what we do here. Try to analyze the system, broad view, synoptic view, try to understand what are the dominant factors that affect the performance of the system, including also second-order effects, because sometimes these effects are quite predominant, quite important, and then come up with a behavioral model that allows to reproduce these effects and use this information, this model, for design purposes. In this case, for instance, using communication networks typically found in commercial products, vehicles, for instance, we're able to reproduce what is received at the end of the chain of the receiver in terms of jitter in the received pulses. Similar application, PLC channel modeling. If you think of a car, now you have a lot of data to transmit. So do we need a special bus transmitting data, or can you use something already there in the car? And the idea of PLC, power line communication, is to exploit the wiring that is already there, that is able to illuminate lamps or whatever electrical objects are found in the car, to transmit data as well. So one of our activities, an example, is to model this channel, including all possible variability. This is absolutely not under control, a lot of variability. And nonetheless, despite this variability, you need to be able to ensure safe transmission of data, right? So The idea here, again, is to do some characterization of template structures, build a model, validate, and then at the end, this will produce a hardware prototype that will reproduce the channel characteristics that one can use to build systems around it. I was mentioning variability. This is another, I would say, very smart formulation of how to handle variability in these systems. Think of having a structure under design. This structure has some free variables. For instance, in this academic case, this is the width of the height of these traces. These are random variables. These are subject to variability even in the production, but these are also subject to variability in the design phase. So how to do it? How to characterize the electrical performance of this object? Of course, you can do a Monte Carlo analysis. You generate 1,000 templates. You do a simulation of these 1,000, then you reconstruct the distribution function of your observables, maybe the crosstalk between the two traces. Or you can do something smarter. If you're able to formulate this as in terms of normalized random variables, then you can expand the equations governing, which are stochastic equations, of course, materials and geometry are random variables. You can expand this stochastic equation in terms of suitable basis function, in this case orthogonal polynomials, and come up with the suitable projection with a slightly larger system of equations, fully deterministic, whose unknowns are the moments of the distribution of your observable. So instead of running 1,000 simulations and collect the results at the end, you can do one simulation once, and then you have the full PDF, the full probability density function of your observable. And the last application I'm showing about this EMC, there's many others, but this is my selection, is about EMI filter design. So suppose you have an appliance that is connected to the mains power distribution in your house. In our specific case, this is switched mode power supply. So anything that is a converter between AC to DC, very often they use this type of power supplies. It is well known that these are very noisy, so if you don't take any countermeasure, you connect it to the network, and then maybe your TV stops working. You receive a lot of interference from this guy, so you have to block it. And typically, you do this using a filter, an EMI filter, electromagnetic interference blocking filter. Of course, those of you that have been involved in designing filters know that the filter works well if it is designed knowing precisely the source impedance and the load impedance. If you know this, then you can optimize the filter performance. So this activity in particular is to characterize inline, while this guy is working, the source inside the device that is transmitting this noise and transferring this noise into the power distribution network. And this is done by this specific measurement technique which has been invented in our group. So we've seen a number of applications in the MC area. Now let me switch to the third area. I'm switching a little gear now because now we go to slightly different systems. I'm saying system, not circuits, because the methodologies that developed here are more general than applied for just circuits. You see the people here, Professor Civalleri, and our rector Marco Gilli, Mario Biei, and the staff people is Fernando Corinto and Michele Bonnin. Here the focus is on complex nonlinear circuits. This is a common background, I would say. And complex systems can be of different nature. One very successful research field is about this neural nonlinear information processing using cellular nonlinear networks. I will be describing that in a second. Mainly you build a system which is governed by nonlinear equation, which is a large number of degrees of freedom, and you design the system such that its solution, its natural evolution, will lead to some pattern in the system that is intended, right? And let me show straight away one application. This shows you a typical cellular nonlinear network where you have a large number of small processors. This could be simple RC cells, a resistor and a capacitor, just. But you have many of them connected in a network, introducing some nonlinearity. And then this can be 2D or 3D. So you can have a huge number of individual objects. And if you think the retina of the human eye or the brain even, connection by neurons, do have this kind of structure. So the idea here is to build template structures which are governed by equations such that the solution of this equation will mimic the behavior of these natural systems. Or they will be behaving to perform a specific task. In this case, I'm showing you an application with a CNN algorithm that is allowing a real-time image processing by active contour tracking, fed by an echocardiogram image, and time after time, or almost in real time, you can do an active contour tracking just by analog computing, just like making the system evolving to the solution which gives the contour of the object, the heart in this case. More generally, instead of simple RC cells, individual components, you can build networks of oscillators. And it turns out again that these oscillator networks represent a bio-inspired computational paradigm. So it's mimicking really the structures that are found in nature. And one of the contributions of our group is to come up with models that are essentially in terms of the phase along the limit cycle of each of these oscillators, which are governed by suitable equations. And you can design, again, these equations such that you mimic the behavior of this brain, for instance, where this brain is doing some specific actions, maybe a recognition of an object, where all these oscillators synchronize in a way that enable this synchronization. This is very fashionable these days, memristor technology. The memristor is a component essentially given by these equations. It's a resistor, nonlinear, where the resistance changes is a function of a variable, which may be the charge. And despite this component was predicted more than 40 years ago, now it is very fashionable because it turns out that one can build these objects and can use these objects for a number of useful applications, including programmable interconnects. You can program the behavior of the interconnect patterns between a number of elements, or even non-volatile memories. So there is a lot of research going on in this field, in this group at this time. The last application is about dynamical processor networks. So circuits are networks. Circuits can be represented by graphs. Networks are represented by graphs as well. And so if you generalize a little bit from a circuit to networks, then you can use graph theoretical arguments to assess the quality of the networks, apply to various scenarios. Can be the internet itself, can be a transportation system, an electric power grid. So you can use graph theoretical arguments to qualify how this network is vulnerable, for example, to failures, or to see other performance metrics of the network. So a number of people in this group are working in this area, so using these theoretical arguments to predict and improve the performance of the networks, maybe by simple rewiring algorithms that improve the robustness to failures. Again, the funding is both public and private with a lot of collaborations. As a last slide, let me show you a number of additional information. We have a number of websites of individual subgroups, Circuits and System Group, EMC Group, these two websites, and then the EM model application is available from the main department website through following the standard links. We have most of the people in our Fields and Circuits group are deeply involved not only in TPC, in technical program committees, but also in the organization of international conferences, both in the antennas and propagation environment, in the circuit environment, and the EMC environment. So we're very active in these fields. And let me end my presentation by showing again the family picture with all faces present. That's all. Thank you very much.